Okay, let's dive into this. Welcome to a completely new way of looking at Cambridge IGCSE Mathematics. Today, we are taking on a very specific role. We are becoming the paleontologist. Now, what exactly does that mean? It means we are going to dig through the fossil layers of complex, multi-part questions straight from the source material, specifically paper code 0580. And we aren't just going to solve these problems. Anyone with a calculator can eventually stumble onto a solution. No, we are going to reconstruct the full, perfect, examiner-approved answer layer by layer, building it up from the very bedrock of mathematical logic. Now, in all my years of analyzing exam performance and breaking down these exact syllabuses, whether it's 0580, 0606, or 4024, I consistently see two types of students who struggle, and it's almost never because they don't know the math. First, we have a student we'll call Alex. Alex is the overloader. Alex stuffs his answers with raw mathematical facts, formulas, and theorems, but provides absolutely zero analysis. He writes down every single formula he's ever memorized in the hopes that the examiner will just magically find the right one and hand over a mark. It's a spray and pray approach, and it fails every time. Then we have Sam. Sam is the rusher. Sam sees a number, grabs a calculator, furiously starts punching in digits, and completely misses the specific command word requirements in the question. Sam loses incredibly easy marks just because of poor exam technique. So in this explainer, we are going to analyze their flawed answers side by side with the perfect solutions. We're going to completely transform your exam strategy by breaking down these exact challenges systematically. We are aiming for that 100% mark potential. Let's get to work.
So, here is our roadmap for the dig today. We're starting with visualizing algebraic patterns. This is all about how we move from basic shapes to concrete formulas. After that, we'll tackle the infamous athlete optimization problem. This is a real-world kinematics nightmare that traps so many students, but we'll crack it wide open. Then we'll master the mechanics of column vectors. And finally, we'll reach the pinnacle of the exam, reconstructing abstract vector geometry proofs. By the end of this, you'll see exactly how the individual pieces connect to form the bigger picture.
Let's start with section 1, visualizing algebraic patterns, moving from shapes to formulas. Consider a classic question derived from our source material. How do simple horizontal lines create complex algebraic rules? Imagine a large triangle. Inside that triangle, two lines are drawn from the top apex straight down to the base. If you just look at that base shape, you can count a total of 6 smaller triangles formed within it. But what happens when we start adding inner horizontal lines cutting across that triangle? I really want you to engage your problem-solving brain right now. How do top-tier students systematically extract data from a shifting visual pattern like that? They don't just guess. They use a highly structured framework. Think of it like the Peel framework: point, evidence, explanation, link, but adapted specifically for mathematics. Your point is the relevant formula or the overarching pattern you identify. Your evidence is the specific, raw data you extract directly from the visual prompt. Your explanation is your step-by-step working out, the logical tissue connecting the dots. And your link is stating the final answer in a way that directly ties back to the specific command word used in the question. Alex ignores this framework entirely. Sam skips straight to the link, hoping for the best. We are going to do this the right way. But before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit that bell icon right now. Okay, let's look at how the paleontologist breaks this down. The key Cambridge command words hovering around this type of problem are calculate, investigate, and write. We have to follow them precisely. The source material explicitly requires us to enter our results into an ordered table. This perfectly aligns with the evidence part of our mathematical Peel framework. We have to organize the chaos. So let's establish our base case. When we have 0 inner horizontal lines, just our starting shape, we have 6 triangles. Simple enough. But when we add 1 inner horizontal line, cutting across the middle, how many do we have now? The visual data provided in the paper shows the number increases significantly. If you carefully count the new distinct triangles formed by that horizontal slice, including the new combinations, you find the total literally doubles. It goes from 6 to 12. Add a second horizontal line, slicing it again, and the total jumps to 18. Do you see what's happening? We are systematically translating visual geometry, drawn lines, into structured, undeniable numerical data. We are building the evidence layer by layer.
Now, let's take that evidence and see how it builds into the final algebraic rule. We have our sequence locked in, 6, 12, 18. What is the explicit pattern here? It's increasing by 6 every single time we add a horizontal line. Now, the command word in the source is write an algebraic rule linking the total number of triangles, which we'll call T, and the number of inner horizontal lines, which we'll call H. If Sam was taking this exam, Sam would rush, see the jump of 6, and immediately write down T equals 6H. Boom, done. But wait, let's actually test that assumption. When H is 0, meaning 0 horizontal lines, 6 times 0 is 0. But our base case evidence clearly proved that when H is 0, the total triangles T is 6. Sam just lost all the critical analysis marks because he didn't link back to the evidence. The correct structured approach reveals that since the sequence goes up by 6 each time, the formula absolutely involves 6H, but we must adjust for that base case. The true, mathematically sound rule is T equals 6 times the quantity of H plus 1, or, written another way, 6H plus 6. If you write that down, you literally see a transformation happen, red pen marks turning into brilliant green check marks.
Moving on to Section 2, the athlete optimization problem. This is framed in the source material as a real-world ICT activity. We are really raising the stakes here by introducing physical motion, multiple variables, and optimization. This right here is where the Cambridge exam separates the good students from the truly exceptional ones. Let's lay out our concrete variables from the source. We have an athlete, let's call them A, positioned in the water exactly 40 meters away from the straight riverbank. The changing station, point C, is located 100 meters further down along that riverbank. We know the athlete's constant speeds. They swim at 4 meters per second, and they run on land at 7 meters per second. The ultimate goal of this entire multi-part nightmare is to find the absolute optimum point on the bank for the athlete to aim for in order to minimize their total time to reach the changing station. When Alex sees a setup like this, he panics and immediately writes down the formula speed equals distance over time 50 different times on the page, hoping it counts for something. Sam, on the other hand, tries to calculate a direct diagonal line straight to the changing station without even factoring in that running is faster than swimming. Neither of them gets the marks.
We need to walk step by step through the logical progression of this problem. Think of this next part as an interactive workshop segment. Imagine a 60-second timer counting down in your head for a quick data scan. Look at the sequence of required steps. Step 1 is straightforward. Calculate the swim time if they go straight. But step 2, this is critical. The command word used is show. Show that the distance P1C is 91.7 meters. Show is a very special command word. It means the examiner has already given you the final answer. They've handed you 91.7 meters on a silver platter. What they are actually testing is whether you can provide the unquestionable explanation part of our Peel framework to arrive there. If the athlete swims perfectly straight to the nearest point on the bank, that's 40 meters of swimming. The remaining run down the bank is 100 meters. But what if they aim for a different point P1, slightly further down the bank? To find the new distances, you absolutely have to use Pythagoras' theorem. You have to prove the diagonal distance in the water, and then calculate the remaining distance along the bank. If you just skip the working out entirely, even if you write down the number 91.7 at the bottom of the page, you will score a solid 0. That is the ultimate flaw you must avoid. Now, stop scrolling, subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @AceTheExams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, back to the math.
Now, what's really fascinating about the source material here is the immense, almost intimidating complexity of the algebraic formula they ask you to validate. Let's say the optimum position on the bank is a distance y from the initial straight line point, and let's call the total shortest time x. The exam paper actually provides this daunting equation for x, which involves a massive square root and a quadratic expression. X equals the square root of the quantity y squared minus 20y plus 1600, all divided by 21. It looks terrifying, but the command phrase here is calculate by trial and improvement or by using a spreadsheet the value of x. This isn't a test of pure algebraic manipulation. It's a test of methodical patience and structure. You literally have to set up a logical table of values for y, systematically plug them into this beast of a model, calculate the resulting x, and narrow down the range until you find the exact moment when the total time dips to its absolute rock-bottom minimum. It's beautiful when you do it step by step.
And remember, as you systematically work through the preliminary stages of that massive optimization problem, you must flawlessly derive and utilize those intermediate values, like the 91.7 meters we talked about. That specific number, correct to 3 significant figures, forms the absolute bedrock of the entire trial and improvement model that follows. If you get sloppy and round your numbers too early in your calculations, your final trial and improvement values for x will be completely, catastrophically thrown off. The examiner will spot the compounding error immediately. Always remember the golden rule. Keep your exact evidence locked inside your calculator's memory, and only ever round your numbers at the very final link stage of your answer. Let's move to Section 3,
Mastering column vectors, translation, and arithmetic. We are going to shift gears entirely now and enter the realm of the abstract. This is where we leave behind the physical realities of riverbanks and swimming athletes and dive into pure structural mathematical translation and arithmetic. Vectors represent the final conceptual leap we need to make in this explainer. Notice the clear comparison laid out in the source material. The exam will always start you off gently with simple point-to-point translations, like finding the vector to move from point A to point B. This is just a basic column vector, a top number showing the change in the x direction, and a bottom number showing the change in the y direction. Very straightforward. But then it rapidly escalates to composite operations. They'll ask, what is vector A plus vector E? Or what is 2 times vector A plus vector B? Here's a quick find the flaw challenge for you. Let's say vector A is 3 over 5 and vector B is 0 over 4. Sam, in his typical rush, will often add the top x component of vector A to the bottom y component of vector B. Sam will look at that and say, well, 3 plus 4 is 7. That is a critical, fundamental error. Vectors have strict boundaries. X components only ever talk to other x components. Y components only ever talk to other y components. It is a rigid, unbreakable structural rule of vector arithmetic. Before we can truly calculate with confidence, we must clearly define our terms, specifically vector magnitude. What does this actually mean? It is simply the physical length or size of a vector arrow. And here is the brilliant part. Whether you are finding the magnitude of a simple little line segment like FG or a massive, complicated compound expression like 4p minus r, the underlying method to find that magnitude remains exactly the same. You determine the final single column vector. You take that top x component and square it. You take the bottom y component and square it. You add those two squared numbers together, and you take the square root of the whole thing. It is literally just Pythagoras' theorem applied to a coordinate grid. Let's do a quick mental speed writing challenge right now. Imagine you have 30 seconds to lock in exactly how you would find the magnitude of vector A, which is given as 1 over 6. The PL paragraph you would construct for this is incredibly straightforward. Point: state the magnitude formula, which is the square root of x squared plus y squared. Evidence: extract the data. X is 1, y is 6. Explanation: do the math. 1 squared is 1, and 6 squared is 36. 1 plus 36 is 37. Link: the final answer is the square root of 37, calculated specifically to 1 decimal place. Why 1 decimal place? Because the source material demands exactly 1 decimal place for magnitude calculations unless stated otherwise. If you write out the full long trailing decimal from your calculator screen, you lose the accuracy mark. The command words and formatting rules dictate your final grade just as much as the math itself. Which brings us to our final section. Section 4, Vector Geometry, Proving Relationships. We have successfully reached the final phase of our syllabus roadmap. This is the big leagues. This is where we take that basic vector arithmetic we just mastered and apply it to complex, interconnected geometric shapes to mathematically prove relationships. This is undoubtedly the hardest part of the paper, and it's exactly where our paleontologist strategy of digging through the layers pays off the most. The source material presents 3 major geometric scenarios to test you. First, a complex triangle where lines are divided internally by specific rigid ratios, like 1 to 4. Second, a square where we have to locate intersecting midpoints and calculate the exact ratio of the resulting line segments. And finally, the ultimate boss battle, a regular octagon where we have to mathematically express far-off sides using only 2 tiny starting vectors A and B. When Alex looks at a list like this, he completely freezes up. He fundamentally doesn't understand how a ratio can possibly apply to a directional arrow. But we aren't going to freeze. We are going to use basic, simple vectors as our building blocks to conquer these shapes. Let's isolate that triangle problem and break it down. We are told there is a triangle ABC. We are given that vector AB is A and vector AD is B. The critical piece of evidence is that point D divides the side AC in the specific ratio of 1 to 4. So the absolute crucial point of explanation here is understanding that the whole entire line segment AC is made up of 1 plus 4, which is 5 equal parts in total. If the small segment AD is represented by vector B, and it represents just that one initial part, then it logically follows that the entire line AC must be exactly 5 times vector B, or 5B. It really is that simple when you break it down layer by layer. But what about finding the vector for the opposite side, BC? We don't have a direct paved path from B to C, so we have to use vector logic. We have to take a detour. To get from point B to point C, we can travel backwards down vector A to get back to the starting point A. Traveling against the arrow means it becomes negative A.
Then, from point A, we travel all the way down the line to C, which we just figured out is positive 5b. So the final vector for BC is simply 5b minus A. We aren't doing impossible math. We are just tracing logical paths on a geometric map.
And this exact logic brilliantly illustrates the ultimate test found in the source, the regular octagon problem. The prompt is, write the following vectors in terms of A and B, FE, ED, BG. Think about this. An octagon has 8 individual sides. You are only given the vector definitions for 2 of them at the very bottom of the shape. To find the definition for a side way up at the top like FE, you have to lean on your fundamental knowledge of the geometric properties of a regular octagon. In a regular octagon, opposite sides are perfectly parallel, and they are exactly equal in length. In the vector world, parallel vectors are just scalar multiples of each other. So if the bottom side AB is defined as vector A, and it's pointing to the right, then the opposite top side EF is also vector A but pointing to the left, meaning the vector to get from F to E is simply negative A. You do not need to invent complex new math to solve this. You just need spatial reasoning, a calm mind, and absolute structural confidence in the rules. The data is clear. Students who implement these strategies, who systematically decode the examiner's command words, who rigorously apply the Peel framework to their math, and who manage their time using this structured matrix, see an average improvement of 2 full grade boundaries. But that only happens if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. I want to hear from you. Drop a comment below with your target grade for mathematics and the biggest challenge you're currently facing. Our team reads and responds to every single comment. Like this explainer and share it with your study partners so you can both level up. Ace the Exams, your Cambridge success starts here. So I'll leave you with this final provocative thought. If you can translate a visual geometry puzzle into a bulletproof algebraic rule, and if you can systematically optimize an athlete's physical reality through pure trial and improvement, what complex problem in your own life can you conquer next, just by peeling back the layers? Keep digging, and I'll see you next time.